have AGNs, star-forming galaxies, particularly dwarfs, population 3 stars, and globular clusters. We switch.
Yes.
Thank you. So the idea of globular clusters, all the problem with them is that they have dynamical evolution on top of their external evolution, and it's not easy to have prescriptions on how they evolved. What would be the UV luminosity here, for example, showed by Mike a few months ago. The evolution of UV luminosity as a function of time is really dependent on the prescription you adopt for the dissolution or even the destruction of your star clusters. Here you see with different, I would call mass loss parameters. On top of that, you have uncertainties on the initial mass function, on the escape fraction of this flux, on the evolution of the mass function of the clusters. The other reason why caring about globular clusters or clusters in general is this star-cluster galaxy connection that you can see in a size, mass, or size luminosity diagram here, with the galaxies being up there and the star clusters being down there. And with deeper and deeper observation, with more systematic surveys, it's now becoming very difficult to tell apart the two populations. We don't have a clear separation between the two families, which used to be here. You can still see a deficit of objects in this region, around 100 parsec in radii. But these gaps are being filled more and more. Another point, which is, I think, very interesting, is that we have this common zone of avoidance, which is actually the fact that you don't have objects in this region there. And this zone is the same for the galaxies up there and for the star cluster there. Is it due to formation? Is it due to evolution? A bit of both? We still don't have a clear explanation for that. But that tells me again that there is a link between how star clusters work and how galaxy works. So basically the underlying question is, do all, some, or any globular cluster form like galaxies? So to have better handle on that, we can look at the initial cluster mass function. And it has been observed to be a power law with index roughly about -2. And sometimes it's claimed that you have an exponential cutoff at la Poisson-Chester that you all know in galaxies on the galaxy side. So this is data, observational data for young massive star clusters in different environments, in different galaxies. Frankly, I don't really see exponential cutoff unless my eyes are guided. But even there, it's not very convincing. The bottom line, with very careful analysis, is that the data is not incompatible with exponential cutoff. So to be clear, we don't know. We don't have the data we need to answer this question. After this initial state, you have internal evolution, so star-stars interactions, stellar evolution, and external evolutions due to the rest of the universe through tides, so that you can change the shape of your mass function. And in a very cartoonish way, if you plot the mass function like that, you start with a power law, like the one you observe, for example, in the antennae galaxies in a major merger. If you want to give you exponential cutoff, that doesn't really matter at this point. And then you look at older systems, like Milky Way, when you have this peaked mass function here. So of course, it's very tempting to say that the antennae galaxies, you have initial cluster mass function. The Milky Way, you have an evolved version of this initial mass function. And to go from one to the other, you need stellar evolution, internal dynamics, and tides. But it's not so clear. If you say that, basically you're saying that the cluster mass function of Milky Way, roughly 10 giga-years ago, was like that of the antennae galaxies today. Or if you generalize, you say that the cluster mass function of young systems looks like the past of the cluster mass function of old systems. But it's a shortcut. It's just an interpretation. We don't have direct evidence for that. And in the end, the underlying question of that is, if I take young massive clusters of the antennae, for example, and I leave them evolved, will they end up as globular clusters as we see in the Milky Way, and the other way around? Was this 10 billion years ago, something like that? So are present-day young massive clusters the analogs of young globular clusters? Well, yes, because they're massive, because they're dense, because at least some of them are formed during galaxy interactions. But no, don't go too fast. You have difference in meticities at high redshift when the globular cluster formed. You have different fragmentation, different feedback processes in different metacity environments. The EMF might be different. I would say it is different. Nobody knows exactly how, but to be surprising, it's not different. We have different external heating. The universe is denser. You have stronger UV flux. You have ionization. And of course, you have a totally different tidal environment due to the different structure in the universe. So, in the end, are present-day young massive clusters the analog of young globular clusters? Qualitatively, of course not, because of all these points. But maybe, if we go to the numbers, these effects have a negligible impact, and quantitatively, maybe they are. The answer will come from GWST, and also from cosmological simulations, which can capture this physics. So high resolution and a lot of physics for that. So if we go back to star formation and try to understand a bit more this process and then to apply that to star clusters, I'm plotting here the Schmidt-Kennicott diagram at subgalactic scale, so something between 100 parsec and 1 kiloparsec scale. We have the local disks here. If you go to higher redshift, but still in the disk regime, you have that. And basically what we have is a roughly uniform with long depletion time. Depletion time goes like that. It's the inverse of a star formation efficiency, if you like. And basically what we have at the low surface density of gas is that you have a lower molecular gas filling factor. So in other words, larger importance of the non-star forming gas in short atomic phase. And that's why you have this little break there. This is due to less supersonic turbulence in this regime. We have shown that with simulations and also with analytical models. We can actually post-dict this distribution of observations here. So basically, it's very tempting to say that if you increase redshift, you just move along this relation, which is roughly the Schmidt-Kennicott power law. However, if you consider galaxies that are more active at forming stars, like the LERs and ULERs, local mergers, they are not exactly in this relation. Of course, you have huge uncertainties on the conversion factor between observables and more fundamental physical quantities through the XCO and alpha CO factors. And these factors are expected to be lower in galaxy mergers. So for example, we played this game using simulations. We computed the alpha CO factor in a technical way I will not bore you with. And we plot that as a function of star formation rate. So we did that with Frederick Borno in the local spiral galaxy, like the Milky Way, in the high redshift disk, a clumpy disk if you like, and also on the different snapshots along a merger, like the antennae galaxies. So here you see the same system at different times. And all these points seem to line up on these relations, but the disks don't line up on the same relation. And the interesting part, I think, is that if you compare the high redshift disk with local mergers, despite very similar star formation rate, you have different physical trigger of your star formation activity, different structure of your ISM, and different CO emission. So all that is due to density and temperature structure of this hierarchical ISM, which is different in massive clumps at high redshift and in galaxy mergers at low redshift. Now, if I look at different regions inside the merger at one given time, I get these red points here. So kiloparsec scale, different region in the antennae-like merger. Same as this one, but a different type at much, much smaller scales. And what you see here is that you have basically more variation of your alpha CO parameter in space from one region to the next than in time between a starburst phase, for example, with high star formation rate, and a more quiescent phase there. So keep in mind these are not the same scale, but still the conclusion holds. And I think this is very worrying for the interpretation of observations because you can have huge variations that are due to the underlying physics of star formation and that we don't really understand yet. All this is linked with the structure of your SM and therefore with the formation of star clusters. Do they form in the monolithic way or in the hierarchical way when they merge substructures, subclusters? Do they form unbound or bound? What the fraction of both? And if we go back to the star formation laws, then starbursts, of course, have a shorter depletion time, so they are above, even with all the uncertainties, even if you are conservative. You are not on the same relation than disks. And this is due to inflows, nuclear inflows toward the center of your galaxy, all the gas piling up there, and also due to compressive turbulence, like it has been mentioned briefly before. And now if we go to higher redshift and also consider short depletion time galaxies, we have the submillimetre galaxies with a lot of uncertainties, a larger scatter here. And the question is, are these submillimetre galaxies actually mergers, high redshift mergers? It's not so easy, as we have heard this morning already, to make the difference between different clumps and different galaxies, pairs of galaxies, for example. So to test this idea, what we did with Jeremy Funch was to make a simulation of two clumpy disks interacting together. So basically, we took all the initial conditions we had for the antenna galaxies, but replaced the galaxies with high fraction, high gas fraction, so they're clumpy, as you can see, and they interact like that. And the problem is that because of all these clumps, intrinsic clumps due to VDIs, etc., you have a strong cusp in your potential. And because of these strong cusps, they generate a strong tidal disruption, and you kind of saturate everything that would trigger star formation at low redshift. So all the usual triggers, inflows, compressive turbulence, shock, etc., all these things, versus dispersion, saturate, and therefore you cannot get your usual boost, your usual starburst in a star formation. So here you see as function of time star formation rate, and the vertical lines mark the pericenter passages between the galaxies. And you see an increase here, the first stronger increase there, but just look at the number, it's very, very weak. You have a boost by factor of 2, while at low redshift for the antennae, for example, you get a factor of 100. So you do have a small increase of star formation, but absolutely not what you would expect because of this saturation. So then, if submillimetre galaxies are not high redshift mergers, what are they? And I leave this question open because I have no idea. So if you now look at clumps, star-forming clumps, and basically star clusters in these clumpy galaxies, this is what we have. So once again, a reference taste is the merger at low redshift, so low gas fraction, and you see it's this number of clumps, or very roughly number of star clusters. It jumps at the pericenter passage, stays up. You can guess here the second pericenter passage is here. But then if you do the same at high redshift with a higher gas fraction, in red, you don't see anything. You don't increase number of clumps, you don't increase number of star clusters, and if you compare to the green curve, which is the same galaxy but isolated, at high redshift again, you don't see much of a difference. So this means that high redshift mergers do not trigger the star cluster formation, and probably they lower their destruction, in the sense that you could have clump-clump interaction, slingshots, and then you eject your star clusters into the halo when you have much lower density, when the wicks are, when the tides are much weaker. You don't have radial migration, but on the opposite side, you also have stronger tidal shocks. As soon as your star cluster has to go through the disk, it will experience disk crossing, it will experience stronger interaction with clouds, with dense gas, and that could have an important impact on survival of clusters. So that's why we need to actually resolve all these physics. And I would say funny illustration of that is a game that Oscar Gertz has played recently. He took a small volume of a simulation, of cosmological simulation, something roughly a very radius of Milky Way-like galaxy, and he simulated it with Eagle resolution and Eagle physics. And this is what it looks like. So here you see the gas density, and he did the same, but at 10 parsec resolution. That's what it looks like. So you can do that because it's a small volume, right? It's only a tiny, tiny volume of the entire Eagle total volume. He chose Eagle, but he could do it with any other big volume simulation. And you see if the rough large-scale structure are more or less comparable, you have, of course, much more fine structures. You resolve cooler gas, you allow more galaxies to form, and if you look at what will become the Milky Way-like galaxy, you see even the disk inclination is different. So if you look in more quantitative way, for example, at the merger trees, time running down, this is the comparison between the two. So as expected, you get something completely different. So your assembly of your galaxy, your in situ versus accreted, your star formation history, your merger rate, etc., is completely changed just by increasing resolution. So if I push the analogy a bit with trees, if you do big volumes, you have a lot of objects. If you do small volume but at higher resolution, you get one object, but with much more details. So if you are studying star formation or feedback or turbulence, as I do, you're interested basically in the chlorophyll of these trees. Which one do you want to pick? So doing this high resolution, we can actually resolve the formation of star clusters, of globular clusters. So this is just moving the camera in our simulation at redshift 9. It's a new cosmological zoom simulation of the Milky Way and its progenitor. It's not exactly the local volume, but it's a bit larger than 1 Virial radius. So everything you see will end up in the Milky Way at redshift 0. It's 1 parsec resolution, 200 solar masses, with atomic and H2 cooling, with star formation, winds, supernovae type 2 and 1A, with, I want to stress that, huge uncertainties on the binary fraction. That could have a strong importance on the type 1A feedback. We trace oxygen and iron enrichment, and we have live relative transfer. And this is killing me, because it's so slow. And the idea was to go till basically the bulk of globular cluster formations, redshift 5 or 6. And 1 year later, we're stuck at redshift 9 because of this live relative transfer, but we can still say things on the formation of the first globular clusters. So this is what we have. And the question we can ask is, do we have comparable physical conditions as in local mergers? And if yes, to what extent? That's again, basically everything that will end up in Milky Way, redshift 9.3. If I zoom on one tiny galaxy, I think it's one of those tiny little dots. You see the scale is decreasing there. You see the stellar component here. You see it has experienced interaction with this guy. You see kind of a tidal tail here. You see some tidal features also there. And if I keep zooming in, 50 parsec in these things, we can see stellar structures inside the galaxies, including these two things, for example. And this little cluster here is actually 4 times 10 to the 6 solar masses, so it could well be the progenitor of a globular cluster in the redshift 0 Milky Way. And this is not new. The idea had been around for quite a while now. The globular cluster could form during interaction at high redshift. But then the question is about their survival. Would they get ejected into the halo? Will they experience weak tides? Could they migrate, participate in the formation of the bulge, maybe in the formation of nuclear star clusters, in these galaxies, in the progenitors, all the progenitors until it reaches the Milky Way? Could it merge with other clusters or subclusters? And we don't know that because we cannot trace the full evolution. But we could have an idea of the full evolution if we decrease resolution, and that we've done actually before. That's again the same volume, but much longer evolution and much lower resolution. 200 parsec only, I would say. So we're missing many of these satellite galaxies I was showing you before. And we poorly capture the cluster property, for example, the size, because we don't fully resolve the gravitational potential at the scale that matters. So all the evolution driven by internal dynamics is not reliable. But what we can do is use a few particles in this simulation as tracers and follow their orbits and compute the tides along their orbits. And that's what we get. Look back time from Big Bang to redshift 0.5. We have taken all the particles, so some of them will be clusters, some of them won't, and we compute this quantity, which is basically the strength of your tidal field, for short. And you see how it evolves with redshift in the Milky Way, so all particles in black, the particles that form in the Milky Way in situ in red, and those that have been accreted in blue, so they started their life in the satellite. And what you see here is that the tides were weaker on average in the past, even for the accreted materials. Even if you form near the central part of the satellite, your tidal field was weaker in the past. And then the intrinsic growth of Milky Way that you can see here with the formation of the disks, the in situ formation there, is the main actor of the secular changes of this tidal field. The problem of this kind of approach is that we're missing all the the high resolution, high frequency terms, but Lietal showed it could be. Okay, so I will skip that. I have to skip that. And jump to my conclusions. jump to the conclusions. Okay, conclusions. Globular clusters tell us about the physical conditions at high redshift and about star formation. We have similarities between high redshift and local mergers with high star formation rates, massive clusters, but also important difference too in metallicity, alpha CO, tides, and probably the AMF. We have gas-rich clumpy galaxies that could form massive clusters, and they do not increase the cluster formation in mergers, but they might reduce their destruction. We need to capture at least 10 parsec, probably much better, less than 1 parsec, physics in cosmological context, so that the whole debate about zoom-ins versus big volumes. We have major difficulties, which I think are turbulence, magnetic fields, stellar evolutions, which is linked to feedback, and stellar dynamics, which is star-by-star dynamics, formation of binaries, multiple stars, etc., that we need to solve before we can claim we actually understand what's going on. And I would say also beware of the EMF. We have likely variations where and when the turbulence changes in mergers and also probably at high redshift. And I stop here. Thank you.
Thank you, Florent.
So many globular clusters display multiple main sequences, so episodes of star formation. So that's got to be one of your bullet points here of what the simulations have to explain.
Yes, yes. I would claim that you need much better than parsec resolution to resolve that, and chemistry and stellar evolution. But yes, definitely.
No problem. So I'm looking at the Finch paper here, with your idealized mergers, and both of the disks together have, or each of the disks you're merging has about 30 billion solar masses of gas, and if you've got a 500 mega-year period of 100 solar mass per year star formation ahead of the final merger, that means the things that you're finally merging have like 30% as much gas available in them as they did previously.
In simulations, not in observations. That's
yeah,
the problem
so
of cosmological simulations.
That's what I'm just wondering, do you think the same effect would happen if you had constant accretion keeping these things gas rich? Or would you see a bigger boost then?
Well, if you keep the galaxy gas rich, then I would say we are more on our side of the story with high gas fraction than on, I would say, the cosmological side of the story when it's more like 30%. And what you have is not really a clumpy galaxy, but a gas-rich spiral galaxy. So I would say the effect, with accretion, the effect is even stronger.
So we find at high Florent, we find at high redshift that actually Lyman alpha radiation pressure is extremely important in dispersing these star clusters, but then we also find that magnetic fields can enhance the formation of super tight bound objects. So can you comment a bit on your radiation transfer implementation and any any hopes to put MHD into these types of simulations?
Can I answer your question in 10 years? I think it's too early to answer that. I have no idea about magnetic fields. I have no idea how that will affect the results. And I have no idea about the results itself, right? The simulation is still running. I would say yes, of course, magnetic fields play a more important role in the denser universe, but I would not dare saying anything else.
If it's really true that the density fluctuations in dust are as indicated by high Mach numbers of 20 or something like that, how close does your spatial resolution come to actually encapsulating that?
So the resolution we have in the simulation, I think, is high enough. We have parsec-like resolution in isolated thing. The problem is when we actually measure the turbulence, and we have to do that with many, many resolution elements. And here we're not really in the 20 parsec, but more in 50, 100 parsec regime. But I would also claim that the Mach number is not the only parameter. Here is more the nature of the turbulence, if it's make it clumpy or more mixing effect. And both could have the same Mach number. So it's a bit tricky there between the solenoidal and compressive mixing.
Okay, thank you, Florent.
Thank you.
Our next speaker is Kieran Grisdell, talking about star formation efficiencies in GMCs.
Hi, thank you for giving me this opportunity. So, as you just heard, I'm going to talk to you about the way in which GMCs form stars. As we already heard this morning, we know that the vast majority of stars form in giant molecular clouds, and so kind of understanding GMCs gives us an understanding of how stars form, where they form, why they form. Now, this is a small problem in that GMCs aren't just one type of object, they're a class